In this video, we're going to take a look at something called, or that I call a chase problem. I know, a little ironic. My last name is Chase, but you get it. Anyway, what it involves is trying to look at a situation that involves two objects that are in motion and how we can compare their motion. So I'm going to take this as actually a problem out of the text, but I'm going to modify it a little bit. So first of all, so instead of 75 miles an hour, let's just immediately convert that into meters per second. So I'm not worried too much about the exact value, but let's say it's 35 meters per second. So police cars at rest and is passed by a speeder traveling at a constant 35 meters per second. And the police officer catches up to the speeder in 750 meters. So let's modify this a little bit because this one is actually a little too easy. So in this case, since we know what the distance is, we can use the distance and the speeder's velocity to calculate the time. And then after that, we can just calculate the acceleration using that time. So how do we make it a little bit more challenging? So police cars at rest and passed by speeder takes off in hot pursuit when the speeder, whoops, this is off the page, sorry about that. Same thing with the 35 meters per second. Passed by speeder takes off in hot pursuit when speeder is 100 meters ahead. And then maintaining a constant acceleration. So let's give them an acceleration. Let's suppose their acceleration is 2 meters per second squared. Okay. So the approach here is that we want to do an equation of motion for both. But before we do that, let's think about what this motion would look like. So I'm just going to go like this, and we'll do a distance and time graph. I'm going to move that up a little bit, just to give myself plenty of space. So time and position, which we will indicate with the letter X. And so the speeder is going to have a head start, and it's going to be going at 35 meters per second. So 100 meters ahead, roughly a 3-second head start. Okay, well, that means that the speeder is going to start off with a y-intercept, and then we'll be traveling with a constant velocity, and the slope of this line equals 35 meters per second. And here's our head start is 100 meters. Okay, now the police officer starts from rest at the origin, but has the gift of constant acceleration, which means that they're going to be going faster and faster, and they're going to be accelerating, which is why how come the slope continues to get steeper. And so this is the when, and this is the where. So find out where and when the police car overtakes the speeder. Okay, so what we need to do is do an equation of motion for each object. So speeder, and we're going to list the variables. So initial position, final position, which we don't know, initial velocity, final velocity, acceleration, And I'm going to put time over here because time is something they both have in common. So we'll do the same thing for the place. And initial position, final position, which we don't know, initial velocity, acceleration. Oh, sorry, final velocity and acceleration. Good. So police officer starts at 0. We don't know the final position. The initial velocity is 0. Final velocity, we don't know. The acceleration is 2.0 meters per second squared. And for the speeder, the initial position is 100 meters. Final position, we don't know. Initial velocity is 35. And the final is also 35 because the acceleration is 0. And so for the speeder, their equation of motion is going to be relatively easy. So x equals, and what I'm talking about is when I say equation of motion, it's this. Okay. So initial position is 100, and they don't have any acceleration but 35 t. And for the police officer, and I'll just put S here as a subscript for the speeder. And for the police, then xp is going to be equal, well, they don't have an initial position, they don't have an initial velocity, but they do have acceleration. So that's going to be 1/2 of 2 t squared. And so to solve this, we set the two equations equal. So, and we're looking for the time at which they both occupy the same position. So this x would be equal to this x. So 100 plus 35t equals t squared. And then we'll rearrange this. Again, obviously, we're going to quadratic formula town, so we'll rewrite this into standard form. Like that. And of course, well, now that we have the quadratic formula, we'll go off to our favorite quadratic solver and type in our coefficients. So 1 up front and negative 35 and negative 100. And you can see our roots are 37 seconds. We'll say 37.7. And then minus 2.7. So back we go. And if you're wondering about the negative 2.7, you can see that if I had extended these back into the negative time zone, that would also be where these two functions intersect. But even though mathematically there are two solutions, there's only one physical solution that makes sense, and that's the 37.7. So, and we can plug that back into either. If we want to find out where this event happens, we can plug in 37.7 here, or we can just square it. And that's what I choose to do. So that is going to be 1421. Almost a mile. So a mile is 1,609 meters. So let's just recap. We write down what's given for both objects, but then each object is going to have their own equation of motion. They're going to have their own pathway here on this position versus time graph. But since the question is, where do they occupy the same spot, where and when, then that means we set the two equations equal to each other. And typically, we're probably going to wind up needing to use the quadratic formula. But using an online calculator is totally fine. Okay, I hope this helps. And of course, let me know if you have questions. I love getting emails from students. All right, take care.